All right. So yesterday, what did we learn about? We learned about Hamiltonian cycles and Eulerian trails and that sort of thing. So you'll find that what we'll do next is kind of related to that, but now, because normally when you work with graphs, okay, so when we work with graphs, you've got lines and dots, yeah, pretty straightforward. All right, you're working with edges and vertices, and these lines sort of, there's no value to them just yet. So you can randomly go anywhere you want as long as you follow the rules of what a Hamiltonian cycle is, or what a Eulerian trail or circuit might be. But now what you're going to learn about is you're going to have graphs that have values on them. Okay, that might have that, and it could represent anything depending on the context of the question. Okay, sometimes the graph, for example, this could be locations. Okay, like on a map, and then these numbers might represent the kilometers or the distance between their locations, or it could be the amount of time it might take you to go through those locations. Okay, so really read the question so that you understand what the numbers might represent and the context of it. Okay, so that's what we call a weighted graph. Okay, because there is weight between the vertices, yeah, and those numbers represent something depending on the context. Okay, so when you work with weighted graphs, there's a numerical value given to the edges. Okay, that's what you're working with. All right, so for example, here you've got a graph. It's got a number of vertices, and you've got your edges. The question here is you need to find the weight of this path B, C, H, D, E. Okay, so all you're doing is if you're at B, follow the path to go to C, H, D, E. So you've got, and I'll highlight this for you. So you've got B, B to C, and then C to H, which is here. C to H, and then H to D, and then D to E. Okay, and all you're doing is you're adding the values of all those edges. So that would be, in this case, B to C is 15, C to H is 16, H to D is 12, and then D to E is 10. Okay, chuck it on your calculator. Remember, we haven't really used our CAS much for this topic because you don't really need your CAS too much for this. You can use your normal calculator. Okay, but you can use your CAS to do like your Eulerian formula stuff. Okay, or the formulas. But that's basically what you're doing when you're adding the weight. Okay, for a certain path. Sometimes you might be asked for the total weight of a graph. What do you guys think that would mean? Add everything together. Okay, so just be mindful. That's what that would mean, total weight for the graph. Okay, so it's not talking about what's the degrees or what's the total degree of the graph. Total weight would be adding everything together in terms of the edges values. Okay, I'm just going to teach this shortest path, and then we'll do the Dijkstra's a little bit later, okay, because it does get a little bit complicated, but we'll just do this. So now, the shortest path, okay, and what it's talking about is what you'll be asked on the SAC is you'll be asked to find what is the shortest path, say, from example, from C to E, okay, or from C to H. Okay, so you have to start calculating what's the shortest time or what's the shortest distance between two vertices. Like if I ask you, what's the shortest distance between B and E? Okay, what would you guys do? B to E. What's the quickest way to get from B to E? Okay, before you answer, you have a few options, yeah? You can go this way, so BFCE. You can go BAHD if you wanted to, but what would be the shortest way? Probably just BCE, okay? But sometimes you got to be mindful that these values could be a bit misleading. Just because there's a straight path that looks like that, watch out for the weight. This could be like 40 on the SAC. So that means BCE might not be the most direct. Okay, so what you're looking for is what's the shortest distance from one vertex to another when it comes to the shortest path. So for now, I'll just show you the inspection method. Basically, that one is just trial and error. Okay? So for trial and error, all you're doing is you're literally looking at every single vertex and every single edge and what's the value between them, and then just figuring out what's the quickest way or what's the shortest. So here we're looking at A to G. Okay, A to G. So that means we're trying to get from A to G. Generally speaking, you always should try and go with, obviously, if you're looking at A, okay, you might want to go with the edge that has the shortest value, which is A to C. Okay, but just be mindful, okay, that the values later on might change. Okay, so I could go maybe A to C, that's 3. Okay, so A to C. So what's next? That'll be 3 plus. Maybe I can go C to D. What will that give me? 9. Okay, and then I could go, okay, have a look. I can go straight to 13. That's a really high value, isn't it? I could go up to E, then to G, because that will only give you 12, which is shorter. Okay, but I could also go, actually, yeah, I could also go D to E, E to F, and then F to G, because that also gives me 12. Okay, so this way is really, really long, so you probably don't want to go that way. So let's check that. So I've got 3. Okay, so that's to E, and that will give me 3, and then E to G. Okay, so adding that up, so far I've got 24. Okay, now can anyone find a quicker path or a shorter path? Is there another one? Yes. Tell me. A to B, good. A to F to G. Okay, so let's add that up. So you went from A to B to E to F and then to G. Okay, so A to B is 6 plus B to E is 8. E to F is 5. F to G is 5. Yes? Okay, so that's another one. From F, you mean?
Oh, yeah,
from E to G. Although it's the same value, okay, it would give you the same. So what does this give us? Also 24. Actually, sorry, 23.
F to G is a 4.
Oh, didn't see that. There you go. Okay, so that one is a little bit quicker by, well, one value. Anthony's right. You could go straight to there too, because it does give you 9, but that's also correct. Okay, either of those work. So that's how we use the trial and error method. Okay, it does take, maybe sometimes you might need to test a couple of paths to get it, but I find maybe 2 or 3 times tends to work. Okay, because by then you probably would have eliminated the ones that won't work. We'll do Dijkstra's a little bit later, but we'll go from there for now.